It's our great pleasure to welcome Jack Merullo. Not quite Dr. Jack Merullo yet, maybe days away. Um, you know, wrapping up his dissertation. So welcome Jack.
Yeah, thanks for the introduction and thanks so much for having me. I think that this talk is going to be mostly about one paper. I don't think I'm really going to like answer or give a very satisfying answer for the title of the talk. I think it's going to be like partly kind of aspirational, and since this is kind of like a familiar crowd for me, I was hoping to like talk a bit about um, maybe the answer to like this question or like the answer to the title. But yeah, so the main thing is that uh, I want to talk about like decomposing neural networks into features. This is like one aspect of interpretability that has gotten like a lot of like over the years a lot of attention, but like I think especially recently like dictionary learning type stuff has really also pushed it up again. I think some text got cut off there, but decomposability meaning just that the neural network predictions can be like broken down into sort of the sum of its parts or into like independent parts of the model. Um, and I think that this is going to become like even more relevant again when more laws like the EU right to explanation law come up. Um, so I think like as language models and neural networks become like a bigger part of our lives, like we'll see more laws like this, and like answering these kinds of questions becomes more important. So decomposability is like really easy when you have a really simple model like this perceptron that does like the XOR task. You can basically decipher exactly what every neuron is doing. This model is like entirely decomposable, but obviously like ChatGPT is not. So this was the I didn't use this abstract, but this was the prompt that I gave it when I gave my like thesis proposal, and I wrote a pretty sensible abstract. And there's, you know, even if we had the weights of ChatGPT, it's a huge ask to try to like decompose the every little feature that goes into like producing this output. But recent work has shown that we can decompose models a few different ways. One way is like on the neuron basis. So a lot of you are probably familiar with this paper, which is about decomposing like the next word prediction into like individual contributions from like neurons and NLP layer. There's like a lot. I could have put like a ton of papers in here. I'm going to talk about a few of these later. So, you know, just pointing out that there's like a lot of work on interpreting individual neurons in like NLPs or attention heads. And then there's of course like the SAE stuff that is like really like taken off in the past couple of years, which is basically like you just decompose some representation into an even larger vector that's much sparser, so that you can try to understand like individual neurons in like a very wide basis. So for example, like it's just a graphic if you're like a little unfamiliar. You train a very wide MLP, and individual neurons in that dictionary correspond to like interpretable features like words ending in ing or chemistry terms, stuff like that. So this talk is going to, mainly I'm going to be talking about this paper, Talking Heads, which I presented at NERVS in December. And it's like really good fortune that Nikhil gave the talk right before this, because like I too care a lot about abstract positional representations. So I think like there's a lot of relevance, and Nikhil did a lot of the heavy lifting talking about like some circuit analysis type stuff. And then I'm going to be talking about some like work that's in prep that I'm like hoping to finish up soon. And those results are still kind of cooking. So I'm sort of showing you some like early-ish stuff, and like I basically just want to talk about that, and there's just like some other things I've been thinking about and like I'm particularly interested in. And more generally at Brown, like the Lunar Lab is thinking a lot about like what we can actually get or conclude from different interpretability methods just more generally, different like circuit analysis methods or decomposition methods. So interested to hear your thoughts on that too. So this paper, Talking Heads, the main motivation for this was understanding like how different components in a transformer like send signals up through the layers. So like how does this attention head at layer 1 communicate to attention head at layer like 20 or something? And this sort of like stemmed from like there's so much circuit analysis work from the past couple of years that just kind of like uses this language really freely. Like, so in this circuit, if you're familiar with it, and I'll talk about this specific task in a minute, but like basically you get some conclusions like, oh, this previous token head, it looks at the, there's an intention that looks at the previous token in the sequence, and then it passes a signal about that to this later induction head, which uses that to then send a signal to the inhibition head. So there's all this communication through the layers from like layer 2 to layer 5 to layer 7 or 8 now. But it's like really undetermined like how that's actually happening through the model. So that was sort of the basic question, which is like when you say something like this attention head is passing a signal, this other head, like what do we actually mean by that? And if if we know that there's like this communication happening, can we like find that connection in the weights? And so another part of this was like I was interested in like weight-based interpretability. So this seemed like a logical place to look, which is like empirically we know there's like communication between these weights. So then can we find it in the weights themselves without any data? And I was thinking about this a lot, and I was rereading the mathematical frameworks for transformer circuits paper from Anthropic from now 4 years ago. And they like just kind of in the beginning are talking about like the residual stream as a communication channel. So this is like a kind of like obvious, I guess, like perspective I'm holding in my head, which is like residual stream, of course, is passing up these signals. But they also have this like really interesting point about virtual weights, which is that because the residual stream is connected through like additive updates, you can multiply out a two weight matrices, like the output of layer 1 writes into a subspace, which is then later, up and up and up through the residual stream is read out by like the input weight matrix of like layer 3 or something. And they derive this like nice composition score formula for this, which is just telling you like intuitively how much does weight matrix at layer 3 reach from subspaces written to by weight matrices at layer 1. And this is just taken by the Frobenius norm of the matrix product over like normalized by the individual Frobenius norms of those matrices. So you get a nice score from like 0 to 1, where 1 means like this matrix is writing only into subspaces or reading, or sorry, this weight matrix is reading like only from subspaces written to by the earlier weight matrix, and 0 means they're like orthogonal matrices. And so, yeah, I was like, okay, this should be such a slam dunk. We should just be able to like take these weight matrices from the circuit and apply the composition score at why has no one done this? And we should just be able to like read off like, oh, there's signals being passed, like that we can just see them without running any data. So we should be able to like see the whole circuit without doing anything. So I was particularly interested in this like one part of that circuit just that I thought was cool in the paper, which is from the inhibition heads to the mover heads, which is just the example I'm going to be looking at right now, which is the inhibition heads write out a signal, which is then used by the query matrix of the mover head. So that the query of that head is impacted by this earlier inhibition head. And so before I like jump into the results, I just wanted to go over some different kinds of composition that can happen. So I showed you this like generalized formula here, which is just abstracted weight matrix 1, weight matrix 3. But there's actually like a few different kinds of composition that can happen with attention heads. Query composition is this one that I'm going to be talking about, which is between the OV matrix of the earlier layer, which is, of course, like if you're familiar with this like terminology, OV is just the its own weight composition between the value and output matrix of the attention head that writes information out into the residual stream. So the thing that writes into the residual stream for an attention head is always this OV matrix. And this writes out information that the queer matrix or the QK matrix, query key matrix, reads from. And so the output of this OV matrix at an earlier layer informs the query, like what to look for in the keys. Like that's adjusting the keys that it most activates to. Hopefully that makes sense. So then you just get this formula, same formula. We're just dropping in the OV and QK matrices here. And so you do this between this inhibition head to the mover head that I just mentioned, and it looks not good, basically. I think that if you just qualitatively, if I asked you to point out like what the so sorry, let me explain this heat map first before I get ahead of myself. So this is the layer and the head. So this is the composition between every attention head in the GPT-2 small here. How much it composes with the QK matrix of layer 9, head 9, which is our mover head. And so if I try to ask you like, okay, we have this circuit, like point to all the inhibition heads from that circuit, like you probably wouldn't be able to find them. They're these ones. Maybe 8.10 is one that you would pick. This I think has the highest composition score, but these other ones don't like look too great. And we look at another part of the circuit. So the composition through to we'll look at 7.9, which is one of these inhibition heads. So just taking a step back from the circuit. Through this time value composition, we get a similar story. Only thing I want to point out here before showing them is value composition is the same type of formula, but it's between two OV matrices. So output from a previous head affects the output of the current head back into the residual stream. So this red signal from the first OV interacts with the blue later OV, producing like a purple signal. And again, we see like the same kind of thing. You probably would not pick these like in-circuit heads as like being, you basically wouldn't be able to find these probably like as the most composing heads. And so maybe the problem is that like, you know, we're just seeing like other circuits, like the model contains like a ton of circuits and we can't just figure out there's like one from this composition score. That's probably true, but just in general, like none of these circuit connections are like statistical outliers with respect to the composition score. Even though empirically we know they're interacting just from this like circuit analysis work from Wang et al. And this is, I did find one other mention of the composition score being used outside of like a toy model setting. And there's kind of the same story, which is that it's basically just very hard to interpret from in like these kind of like real models, even though GPT-2 small is so tiny, unless you have like a toy model, the composition score doesn't seem to be very useful on its own. And so the kind of like hypothesis I had after that was like, well, every matrix is just like, you know, full rank. It's writing out into like every little like subspace, and every matrix down the road is also just like reading from every little subspace. So maybe like if we decompose the matrix to like, you know, smaller, the subspaces that it's writing out into, maybe we can try to like isolate the signal that way. And so I used the singular value decomposition on the OV and QK matrices to do this. There's a nice identity you can rewrite the SVD with, which is you just rewrite it as the sum, like element-wise sum of a bunch of rank 1 matrices. So this gives you this like big stack of rank 1 matrices that when you like collapse them all together, you get the original matrix. And with attention heads, this is also really nice because you get, because the head dimension is usually a lot smaller than like the residual stream dimension, you get fewer of these matrices that you actually have to care about because the rank of that matrix is only full with respect to the head dimension. So you only need to care about like in GPT-2 small, there's only 64 of these matrices. So it's actually pretty easy to like search over them. But like, then what do we actually do with these component matrices? There's kind of two things we can test. One is the, I just talked about the composition score between matrices. The obvious thing is like, let's just use these component matrices to do take the composition score with these component matrices instead of like the full matrices. And so there's like a weight-based metric that we can use. So this is again something like this where we one at a time. So the choice here was to take one component matrix, so in this case this red one, and take the composition score between that and just the full like later matrix. You could also just take a component matrix from this one. But that felt like wasn't actually necessary because like, we wanted to see if anything out from coming from here is particularly writing into this one. So that was the choice there. So it's the same exact formula. We're just using this individual matrix instead. And then the other thing we can do is that this also gives us a really nice like model editing procedure. So we can test the behavioral effect of a given component matrix by swapping out, or just rather removing one of the component matrices from the sum. So this is just rewriting the weight matrix, but without the ability to write out into that subspace. And so I kind of like very, very briefly went over the IOI task, but to understand like what we're measuring when we remove this component, I need to talk about what this task is actually like. And so the goal here is just to generate like Mary over John, the intended indirect object over the other subject token. So we call this S1, S2, subject 1, subject 2. And Mary is the intended indirect object. And so the circuit that they found, like the original goal of the Wong et al. Paper was let's find the circuit for like how the model knows how to do this. And so a key part of this is that the mover head, which I kind of talked about earlier, like 9.9, other such heads in the model, they attend to the name that they want to copy. And so, for example, the mover head will attend to Mary. And as a result of attending to Mary, the next token is more likely to be Mary. If it attended to John, then the next token would be John. The part of this circuit that I was interested in is the interaction between the inhibition head. Let me go way back actually. The interaction between the inhibition head and the mover head. The inhibition head is telling the query to inhibit the John token and instead prefer the Mary token. So just say attend less to John. That's the signal that's being passed there. And so as a result of inhibiting John, like I said, the mover head's more likely to attend to Mary. And so the score we can take directly out of this is like the mover head attention to the indirect object versus the subject token. So without any inhibition, the mover head would attend uniformly to John and Mary, 50-50, and thus produce like, the resulting next token prediction would be kind of like randomly chosen between John and Mary. So the score we can just take is like the attention to the indirect object minus the attention to the subject between these positions. This is just fully based off of the previous work, which found that these interactions were pretty predictable. Does that make sense before I keep going? I kind of like glossed over those components. Cool. So again, those are the two metrics we're taking as a weight-based and the behavioral score. And so what we found was one at a time removing the components, or one at a time testing the composition score between the components. We see like there's one component in particular that has a like very outlierish high composition score, which is this blue X here. And the result of removing that component at the same time has a very disproportionately high behavioral effect on the inhibition score. So here again, lower inhibition score means like more even attention to John and Mary, or the subject and indirect object. This is averaged across a larger data set. And so it seems like there's this one component that seems to really stick out here. And we can actually get a signal from the composition score that corresponds to a real behavioral shift as well. And there's 4 inhibition heads in the model that they found. And we found this effect basically with all of them. There's one or two components that look like this. Particularly, there's one that has like a really high composition score. The one exception being kind of like 7.3, I'd say that there is still one, but like just the general effect, it seems like this inhibition is just generally less important for the model entirely. So we see less of a behavioral effect. So for future analyses, when I talk about some of these, we kind of cut out 7.3 because it just does see when it's convenient, just because it doesn't seem that important. So the kind of like conclusion from this is like when Anthropic was talking about like, communication channels between the residual stream, what we found is that there seems to be like a rank 1 signal in these cases that in which this is occurring. So maybe another way to say this is like the communication channel between these layers is extremely low rank. It's like just in this one direction, basically.
Maybe you have already talked about it, but could you describe it once again? What was the motivation for applying the SVD on the weight matrix instead of doing it on the residual stream itself?
Yeah, because we were talking about, I mean, that you could do it on the residual stream itself.
Yeah.
Because I was interested in particular weight, like just weight analysis, I wanted to find the signal in the weights, like somewhere in the weights of the model. We already knew the circuit ahead of time, so we knew which weights to look at, which made it really easy and convenient to know which ones to look at.
Okay.
And the specific choice of the SVD was kind of like other people have done it.
SVD is fine.
Yeah, it tends to find interpretable things for whatever reason. It seems to be somewhat SVD line. But in that, the reason for that one instead of like other decompositions was like the SVD just has a lot of nice properties. Like it's ranked by variance. Each one of these component matrices is orthogonal to every other component matrix. So by removing it or changing it in some way, you're not actually affecting any other part of the weight matrix, which is really nice. And what else? Oh yeah, these matrices are just all like, since they're outer products, they're all rank 1, so you're only affecting like one direction. So it's
Yeah,
also
if you do the similar analysis on the residual vector itself rather than the weight matrices, I feel we may end up getting these 3 results as well.
I think you would get the same results because
Yeah.
because you're getting just the accumulation of all of the outputs of all weight matrices, so they have to be in there. And I imagine just like looking at a task specific level, like the residual streams on this task, this must, as I think, be a high, like a large component, like in the activations.
I'm not sure about that, Jack. Yeah. So I feel like it's it might be a good appendix for this paper to like measure against baseline, because I kind of suspect that your weight-based decomposition might be superior in some ways to an SVD that's just based on pulling out major components of the variance of the residual stream.
Yeah, that was my question.
Were you here for the, I think it was, what's his name, the Pan paper, the one from Transformers and Vision, where he's doing the decomposition of attention heads in vision transformers? You guys remember that talk, right?
Interaction.
What?
Query key interaction.
Yeah, the query key paper.
I have seen the paper, I'm not sure.
Yeah, you maybe missed the talk. Yeah.
Yeah, but my question was similar to that. I mean, if you can get to the same result by analyzing the residual vectors, then why did you go for the weights? So
You need no data.
you need no data.
You don't need the data yet.
See, yeah, okay.
But besides that, right? So the query key business is it's this weird thing. It's a bilinear form, and taking an SVD composition of a bilinear form is a special thing. It's different from taking SVD of the data. And so it might be that there's something that like there's some new insight about doing that.
And yeah, I guess you did mention like in Nikhil's talk also like you would find clusters for like gender, which is not necessarily like
Not the task.
not the task.
Yeah.
But it is creating a lot of variance in that. Yeah, so that's true. Actually, I might be assuming too much of these. But so yeah, it'd be interesting to think about that. So I'm gonna talk a bit more about how these like individual components. So we have, again, like 3, maybe 4 inhibition heads that I just talked about. So it's like a few different components that seem to all be coordinating together. I'm going to talk a bit more about that coordination in a bit. So did you have a question?
Oh, yeah, I was just wondering what you think the direction represents. Like, so if it's just 1D, it's just saying.
Yeah.
It's just like a 10 more to, like, is it like a positional thing again, like Nikhil's stuff?
It's a positional thing. Again.
Yeah.
So I'll talk about that.
Okay.
Yeah, totally. Yeah. So before talking about, okay, I'll talk about that right now. So since it's each of these component matrices, I kept them in matrix form because it's like really just convenient. You can just plug it into the composition score formula, so we didn't have to change that at all. But really, like, since it's rank 1, it's really just like outputting onto one direction. So it's really just a vector representation. And so what we can do is like intervene on this space. So we can overwrite the output of the attention head to just be like the vector that's this direction in space that's being written out times some scalar. And this is our just like intervention on like how does scaling up and down this direction space affect the prediction, affect the query specifically. And we found that it is a positional signal, and it's not really shown in these results, but I can say that it's a relative positional signal that tells you to either attempt to name 1 or name 2. Basically, what this is showing that if we flip the names, the order of the names, and we just scale up and down, we can control whether. So this is the inhibition score still. We can actually get the model to fully attend to like one name or the other, or not fully, but like basically fully prefer one name over the other. And it's purely based off of attending to like the name in the first position or the second position. And it's this weirdly smooth curve. I was really kind of surprised by this result that it's like so cleanly interpolating in this head. So yeah, any questions about that? Okay. So that's what we found that this head was doing. I can show the other heads as well. They had the same pattern. Control heads, like other random heads, did not have this pattern. Or random components within other heads, and even within these heads didn't have this pattern. So the next thing I guess is that like, okay, so it's just going back to like this number specifically, the composition score. That was again a behavioral result on like scaling it up and down. But I showed those heat maps at the beginning, which were like not looking so great for the composition score. But if we think of the composition score now instead of in the component basis, we can look at for each head, we can take the composition with like 9.9 again, but for each head, only plot the like max composing component within that head. So for each head, we take the composition score between each of the 64 components and just only plot the highest one. So I'm going to, again, just go back to showing heads composing into component 6 of 7.9, which we also know to compose very strongly to the mover head. This is what I showed you before. So these are the duplicate token heads and the induction heads composing the 7.9. And then when we decompose it specifically into this component, which we know to be important for the other part of the circuit, we only get the in-circuit heads like really popping out. And so what this kind of tells us is, yeah, so this is just showing that. I need to come back to this. I want to jump to this slide actually. So the nice result from that is like we can go to 7.9.6 to find things leading up to like this point, and then continue onwards to like 9.9, doing the same kind of strategy, 9.9 component 0. And we find a few out of circuit heads really composing with this from other circuits. We actually look into those heads in the appendix. But basically we can find like almost the whole IOI circuit like directly from the weights without any data at all. Of course, we know that the circuit is there, so that's how we know like verify it. But there is in fact like a weight-based signal that we can like get out of this just using the components. And if I go back a bit, if we focus just on the duplicate token head 3.0, you can also look at the components within 3.0 that communicate with 7.9.6, layer 7, head 9, component 6. And you can look for if there's, well, is there another like low rank communication channel? I kind of only talked about one. up to this point, were just inhibition heads to mover heads. We found like more evidence for like low rank communication channels. And in this case, I'm showing a slightly different visualization, but this is each component and the composition score between these. We found two that are like really large outliers, not one this time. And if you plot the activations projected along these component directions for random tokens where some are duplicated and some are not, they seem to like nicely separate duplicate from non-duplicate. Like both of them seem to have some signal for this. Why it's two instead of one, I don't know. I don't really know if it's that important, but like with some noise, it is seemingly separating these quite a bit. And then again, we can influence the inhibition score all the way back from layer 3 by just changing this signal. So in this case, since it's two dimensions, or like two directions rather, we're kind of like going, I'm scaling them both at the same time. It's kind of like diagonally, like along both axes, either positive or negative. And again, you can get this like kind of crisscross shape, which is controlling attention to either name 1 or name 2. Although the absolute impact that you can get from doing it so early is a little bit less, probably because there's a few other signals that we're not accounting for. So before we could get it like really, really high, attending to one name or the other. And in this case, we can only get it to like kind of slightly prefer one or the other, but we're at least getting the cross shape that we expect. Versus this is the same head and two different components, the 0th component, which is actually the highest variance component, and the 4th component, like our index 3 component. And we don't see that effect at all. Why there are these like little bumps, I don't know, but like something caused that. So just here's another, just a zoomed out view of that signal. I usually don't have time to talk about it. But I showed you these components to 9.9, like the highest composing components with 9.9. And I pointed out that there's a few here that are not in the IOI circuit, but are still highly composing. So we do some investigation, we do some like kind of preliminary like circuit analysis on these heads to see if they're anything interesting. And it does seem like they are part of a novel circuit that has something else to do with like context retrieval, similar to this inhibition mover subcircuit, but has more to do with like retrieving like semantically related items from context, which is, so it's like qualitatively like very different from inhibition or mover headness land a little bit. So the details for that are in the appendix. We didn't arrive at like a super conclusive thing. It would require like a whole circuit analysis, I think, to do that. And we just didn't have the space, I think. So, but yeah, some cool results there. So that takes us to like, okay, this is nice. We at least, I mentioned this like relative positional signal in one dimension. I think this ties back nicely to like Nikhil's result on the like low rank signal controlling positional, relative positional signal in the like the least task. So we only showed this for like 2 names. So then the question was like, okay, like what is this? What are these heads doing in general? Like these specific components, what are they doing in general? Like on arbitrary data, like what does scaling this up and down do? Like what are they generally responsible for? And we basically just looked at like attention patterns on these heads on like a wide range of like just open like text corpora and just looked for patterns. I specifically looked at like the top like the most active patterns when when these heads are attending to like the non beginning of sequence token. And the pattern that was like very, very consistent was that is attending to words from like things like the word and to previous items in a comma separated list, or multiple choice questions, kind of like anti-repetition patterns, and things like that. So basically the kind of intuition here is that if these are in inhibition heads more generally, what these are doing is like attending to previous terms to avoid just like repeating them. So you don't want to say dopamine, serotonin, and dopamine. That wouldn't be good. So we kind of think that's what these are responsible for. And to kind of study that more, we came up with like a kind of toy task, which we call the laundry list task. And the idea is to predict, it's a leave one out task. You give it a list of items and then you kind of repeat the list in some naturalistic way. And then the model needs to predict the like remaining item that hasn't been repeated yet. And so it's like, you say like, okay, I'm going to go to the store. I need to buy a plate, pear, and a pen. First, I'll get the pen, the pear, and then I'll get the blank, like the plate is the remaining item. And these are randomly shuffled each time. So the second order is always different. So it's not just you can't just use like an induction head to complete the pattern. And it's really easy to scale the number of objects. You can have like, 20 items on your laundry list or something. So, we take a look at this task, and the model is pretty good at predicting the last item up to some number of items. But now, since we kind of like know something about these individual components within the weights, we kind of do the same test that we already did, which is like scaling up and down the activations along these directions. Again, going back to the idea that there's like coordination happening between the individual components across the multiple inhibition heads we have. And so what we do is like basically plot each inhibition head singular vector, which corresponds to the important component on some plot, like on this like 3D space. And we kind of just like move around the activation in this 3D space and see how that affects the mover head's attention to the remaining items in the list. And what we find is that like we get this kind of smooth interpolation between like, item 1, item 2, item 3, up to n items. So basically this subspace, this 3D subspace is controlling the attention to like the item in the list. And this is again a relative, it's not an absolute position because these prompts can have like varying number of tokens. So like the prompt formats like are different every time. So they're varying by a few tokens. And it's always moving the attention between the like list items. So like lighter orange and bottle or like pear, pen, plate, like things like that.
Can I ask how you find the path in the 3D space?
I did a really large, I have a figure that might like visualize it nicely for you, but basically like I just swept this whole space, like, took different like every 10 or something every 5. And I found the spot that's like most attending to item 3, most attending to item 1, most attending to item 2. And I just like drew the triangle, then interpolated. Yeah, so this is that figure. Basically, like each dot is a point activation space that I tested, and the color is the most attended to object in that part of the space. And so this is with 5 objects, and you can see it's like actually really nicely grouped. Where this is all attention to item 1, item 2, 3, 4, and 5. It kind of like goes around. And as you add more items, so this is the one I just showed you, and this is with six items, and it like splits it at a certain point. Something that seems to happen, so people have talked about like primacy and recency bias in models, which is like preferring the first item or preferring the last item. Humans have this bias as well, which is maybe how the humans got it because they're trained on our data, but that's speculation. What seems to happen is item 1, this space seems to like never get broken up as you add more items. And this space, so this orange space and this purple space, both cases correspond to the very last item in the list, regardless of like the number of items. And it doesn't seem to get broken up basically until it like really needs to be, I guess. What needs to be means here is kind of weird, but like it always comes at the time, seems to like split things up in the middle items. And I'll show some more examples of that in a minute. But basically like this plot is showing with GPT-2 the accuracy as you scale up the number of objects. it decreases like very, very rapidly, even though the difficulty of the task is essentially the same. I think there are more distractors to be fair, but like, there's this attention mechanism is not like losing information. It always has perfect information of the whole sequence. So it's kind of not surprising that it gets so much worse as you increase the number of objects, but there's not really a good explanation for why. And so one way we try to explain this is that, well, okay, if you go up to like 20 objects, like here's item one again, it's taking up this huge portion of the space. And it's like splitting up like this little corner into like, 15 different objects. So the error tolerance for the mover head to attend to any one item is like super low now. Like it has to like, precision strike this one little like yellow spot if it wants to attend to like item 14 or something. So that's kind of what we think is why one reason why the accuracy goes down. We're able to somewhat validate that with this like really manual intervention where we hard code if we know that the answer is going to be like item one, we hard code the attention to be in like this part of the subspace corresponding to item one or like item 14 or something. And we can like pretty significantly improve the accuracy on this task across the number of items. We don't fully fix it, but like, for example, the item 10, like 10 objects accuracy after the intervention is actually higher than the original model's like 5 object accuracy. So it improves quite a lot. The kind of summary here is that like we find evidence that models are communicating through like these specifically low rank communication channels. And in the inhibition mover subcircuit example, which is just one that I was particularly interested in, it seems like this communication is like entirely content independent. It's basically a mechanism for like acting like as an indexer in a list. When the model makes the key vectors for the items in the list, it's assigning something like, hey, I'm item one, I'm item two, or something like that. And then the query is able to index those specific keys in a sort of like position independent way, or absolute position independent way. So that's that paper. I have some ongoing work that I want to talk about, but I'm happy to take if there are any like questions right now about this one. I'm happy to answer them.
It's in RUI paper, I think they mentioned that there's inhibition heads also include some form of, at least to some extent, the token value information as well.
Yeah.
How do you take that? How do you think about that?
Yeah.
Based on this.
Right. So like answering it maybe only under the perspective of this, I would maybe expect like the token value. So the IOI paper, for example, I think is what you're referring to, also finds there's like they find that it's like strongly passing a positional signal as well as a token value signal.
Yeah.
Although predominantly positional.
Yeah.
And so if I had to guess, if we wanted to like find the like token value signal that's also going through these heads, maybe it's just through other components, and how large that subspace is that's storing like the token value, like the identity of that token, I'm not sure. I think that's like like you were talking about doing like a binary mask like learning procedure. I think that would be a cool way to actually find that. I remember also talking to Sheridan about like the sub embedding space being in like an induction head, like moving token values around. So it's like I think like still a lot of work on that. I don't know the exact answer, but that'd be my guess is like that's where I'd look at least is like try to find some subset of the components that are passing like token value. How important that is for the prediction. I like how the model decides what's important for a prediction. I don't really know though between those two signals.
Just out of curiosity, for the rank one matrix that you find, is it normally in like the top like 3 singular values, or can it be like much further down?
That's a good question. It seems like there's a bias towards. Okay, so here's like the duplicate token head example. This is like, so we index at 0. This is which one? 1 and 2. Yeah, 1 and 2. So the second and third, which are high variance, but not the 0. And then these ones are, this is index 1. I know you can't like read these, but this is index 1. This is index 6. So like the 7th. most important. This is index 2 and this is index 1 again. So it seems biased towards the beginning, but not necessarily like the 0 or something, like the highest variance. So I don't really know if there's any rhyme or reason to that. It might just be.
What are your thoughts on using the weight interface methods, the blind section, where you don't know the
Right.
circuit?
Yeah, in a totally blind setting. My thoughts for I'm gonna bring that up again, and I am also just curious in like other people's thoughts on that. My thought is that like it's a good way to reduce your search space in a completely blind setting. It would be great to be able to reach some solid like interpretable insight just from without running the model. So the nice thing that you can find all the connections between all the weights this way. And like particularly like strong connections like that you would actually be interested in. There are other things that you could like mix into the process without running the model, like for example, doing like logit lens on rows of the weights, or even the components themselves, like the singular vectors you can do logit lens on. Actually, people have done that and they're highly interpretable, tend to be. You could say something like, oh, this head is connecting really strongly with this specific component, and also this specific component outputs like the names of mountains like really strongly in the output space or something like that, whatever that means. But like that, then you have some idea of what that circuit is already. So I'd be curious about introducing the connections between the weights with other like weight-based interpretability stuff. For example, there's other stuff on like you can find a mover head by looking at the diagonal of the OB matrix. If it's like really positive, or if it's really negative, then it's a negative mover head, like demotes concept, whatever it attends to. So that's like, I think that's about as far as you could get in a totally blind setting. I think there's probably like a lot of room to grow. Curious about if other people have ideas on that later.
So you think that there's more work that needs to be done for validation of the circuit that you find?
Yeah, I think in general, like you're definitely going to want to actually run them all at some point to validate your findings, right? But like, there's maybe settings where like you have some feature vector, or like from an SAE or something. You know that this is like a feature you care about that you can look at without running the model. What components interact with this singular vector? Like which ones are, if I were to steer this, what components would actually like react to? So that's another. I'm gonna go like really quickly through this. There's not like actually that much. Like I mainly just want to like talk about what the idea is and like some things I care about studying, but there's not so much to get into. This is work that's being led by Alan Chen, who's a student at Brown undergrad. And the idea is to like, we want to study like universality of model features, particularly like, across model sizes. And one thing that people have done since like 2015 or something, although I don't think people do it that much for whatever reason, is model stitching, which is the idea that you learn a projection between the representation spaces of two models. So this can just be like the middle layer residual stream, a 1B model and a 7B model, let's say. And you just learn a projection matrix P, maybe plus a bias term. So it's like an affine transformation from one representation space to another. With the idea that you can run like the first half of the first model and the second half of the second model, and you get something that's like coherent. Like you get something maybe like the performance of like something in between the two of them in terms of like your distribution of tokens or something, right? And so we train this projection in this specific project. We train this projection layer with like an MSE loss, like of just reduce the mean squared error between the two representations, like the stitch and the ground truth. If you were to run like the first half of the 7B model, once you have this projection matrix, this is just mapping from hidden size A to hidden size B. There's a lot of stuff you can do with that by itself, but sparse autoencoders are a really nice way to decompose your residual stream. And so one thing we can do is just pass the weights of the sparse autoencoder through the projection matrix. So like the encoder matrix rows, like the decoder matrix rows or columns or whatever. You can just pass those through this projection layer, and now you have a sparse autoencoder for model B, basically without training it on model B at all. And so if this works even like a little bit, then you can say something about, and like the activations like correlate to each other, then you can say something like, okay, these are learning really similar features or maybe really dissimilar features. And what we found is that generally you're don't worry about the difference between stitched and seed stitched. Seed stitched is kind of like a little bit like a skyline. It's like two random seeds of the same model stitched into each other, versus stitched is between a model A and a model B, which are two different sizes. All these models are trained on the same data, by the way. That's also an important thing I should mention. Meaning the question we're kind of asking is like specifically about features learned by models of different sizes. So that's something to keep in mind. Generally, we find that the features correlate really, really strongly. So compared to like a random baseline, which is a very low baseline, we get a pretty positive correlation between the activations of individual neurons in the SAE. This also lets us do it. Yeah.
So your correlation is between you stitch an SAE over through your stitch transformation, and then you're correlating them with what, with an SAE just trained in the new setting. Is that right?
So it's I glossed over that. So you have SAE on model A, which is trained on model A, and you can get some distribution of activations over just text for all the neurons in your SAE, and then you stitch it into model B, and then run the same text through model B through your sparse autoencoder and get the distribution over neurons.
So each of the transferred directions,
Yeah,
it is responding to the same text in about the same way as it was in the original model.
yeah,
I see.
that's the idea.
I see.
And it's hard to really evaluate that. I think that's currently a point of it can be fleshed out a bit more because
And then for your random baseline,
Yeah.
are you taking like an untrained SAE and doing the same thing?
yeah, you can do a couple different things like random SAE pass through a trained stitch or a random, like a trained SAE through a random stitch.
Yeah, so to me, the interesting thing would be like a random SAE through the same trained stitch.
Yeah.
And is that what you plotted here, or is that different?
These are random, it's both actually. So random SAE is this orange one.
I see. Through the same stitch.
Um,
Richards.
question, conceptually, because I'm not really as familiar, like, what's the difference between this and a sparse cross-coder?
Yeah, we started working on this before cross coders came out. They are different though.
Okay.
Like one way you could answer this question now is probably with the cross coder. Although there are kind of important differences where you are specifically optimizing for a shared feature space with the cross coder, but they're conceptually pretty similar. Yeah. There's a couple nice things that you can get out of this approach though, which I'll talk about. So one thing you can do, which we were really interested in the fact that this worked, is that if you have a vector that successfully steers model A to produce Spanish text, you can pass this through your stitching layer. Oh, okay, I'll answer that question in another way actually right now, but let's keep that in mind. But you have some vector, which maybe you get from your sparse autoencoder, which steers Spanish text. You can pass that through your stitching layer, and now you also have a steering vector on model B that also produces Spanish text. And so another part of this project I didn't mention, we have been kind of focusing on sparse autoencoders, but this works for any way that you can get a steering vector. You can pass it through this stitching layer or whatever feature vector you want. So, you can the point is that the stitch is able to like map these representation spaces well enough that if you had a difference in means steering vector, you could also pass that. But that's still something we're kind of figuring out. So we were interested in that kind of result. We also found that if you wanted to have a sparse autoencoder on both models, you actually get a really large flop savings by doing it this way. We're still evaluating how good these SAEs actually are. So we're running on like SAE bench and stuff. but basically you get, if you, initialize your sparse autoencoder and then continue training it, you get, about a 2 times, or about a 33% flop savings training the stitch and fine tuning your initialized SAE rather than training the SAE on the small model and the big model separately. Which is maybe a nice way to kind of like bootstrap a bunch of SAEs like very quickly. But still looking into that. I'll kind of end here. The kind of like things I'm really interested about that kind of fell out of this are these like features that don't map well. We call them like bookkeeping features because we think they're like storing like metadata. A good example would be like the kind of indexing feature I just talked about, like in the Talking Heads paper. So we found a few that are like this, and they map well to, yeah.
Sorry, what's the effective null space of the unembedding matrix?
Yeah, I can explain it. Basically, the idea is like from this paper, and also actually there's a Wes Kearney paper about it too that also talked about it. It's like the effective null space is basically you take the unembedding matrix, you do the SVD on that, and there is a long tail of singular values that are like basically zero. And so if you write into those directions, you're not affecting the logits at all.
Yeah.
So if you are outputting features like into that space, that's doing nothing for your next token prediction. And the idea is that, well, they're probably doing something. This paper showed that they're controlling like confidence regulation, specifically in like the neuron basis. So for example, like changing the entropy of the next token prediction without changing the like ranking of the next token distribution, basically. And we found that these features that are like high norm and like high density are also like high cosine similarity with this effective null space. And seem to be doing something kind of similar. Like there's a mix of them that are confidence regulation. There's maybe some that are like deactivating attention heads. You know, we found this through the SAEs, but you can also maybe find it in the neurons. So like really is like they're a better, they kind of like kind of tangential question is like, is this better to look at the SAE features or the neurons? I don't really know. I'm kind of like curious about that, but I'm also just curious about these features in general that exist. That it kind of like goes to like the kind of broader point of like, it's really nice to look at these features that if you were to actually like gloss them, look totally uninterpretable, but are in fact doing something. SAEs can give us that, but maybe also neurons can too, and like maybe weight decomposition can as well, like with the indexing thing. I don't know like what we can get out of each of these methods that's really different. And it'd be really nice, I think, to figure out like the advantages, disadvantages of all of those, and like what kind of guarantees we can get out of some, not others. So that's kind of, you know, leading off on kind of a like shrug point, like this is kind of what I'm thinking about now. Yeah, that's it.
It's an amazing body of work.
Thank you.
Thank you. Thank you, Jack.
Yeah, thanks.